Right, welcome to my series on my homebrew CPU made out of logic chips. I'm designing everything on small PCBs so I can change them and swap them in and out, rebuild them as necessary. So the first one I made was this one, which is the Arithmetic Logic Unit. It uses two 74HC161, which are these two chips here. Since they work in reverse logic, i.e. normally you'd have 5 volts equals 1 and 0 volts equals 0. These work the other way around, so I've had to install some inverters to convert those back to the way the rest of the computer is planning to work, with 5 volts 1 and 0 being 0. Right, there are two input registers, so we have A and B, and an output which is C. And if you notice here, I've set some LEDs up to show what it is. So at the moment we have A is blank, is 0, B is 0, and C, because everything else is off, is actually a decrement of A. So 0 minus 1 is minus 1, which is shown in 2's complement format with all the lights set up. Okay, let's go into some of the functions available in this ALU. First of all, let's do an not function. In this case, I'm saying anything in A, not anything in A, goes in C. So if you notice, any light that's lit here is not lit here. So it's the reverse of the other. Again, you can do a similar thing with the B register. Anything that's not B is in C. The OR function. We have A or B, in this case it's lit. A, there's nothing in B, but it's lit because one of them is present. This one has nothing because neither A or B is lit, and so on all the way. Going further, we have the AND function, which is only lit when A and B are present. So the two places are here, and in those two places they're lit. Add. In this case I've got a value of 57 here, and I'm adding 23 in, which then gives us a value of 80. We also now have the same values, but I've also had the carry in set, which effectively adds 1 onto the end. In which case the value here now is 81, in binary of course. This time we've done a similar thing, but I've added together 127 plus 200. Which is greater than you can hold in 8 bits of 256. So this light, the carry out light, is on, and that represents 256. And the remainder, which is this bit here, is shown in the register C. The subtract functions. We'll have 170 minus 10, which leaves a value of 70. For the registration functions, the subtraction functions, the carry must always be set. Also, you'll notice that the carry out light is set because the A value is greater than the B value. therefore it sets the carry light. In a similar way, if I was to do 170 minus 170, the carry out light is set and the equals light is set. This gives us the, this means the two values are equal, and we can use it as a comparison. This time, similar thing, but the carry out is not set and the equals is not set because the value of A is less than the value of B. Now you may be saying, so in this case I've got a value of 10 and I'm taking 52 of it, 2 away. That gives the value of minus 42. Now at this point I was going to make some joke about being life, universe and everything, but I'll leave that for another time because I couldn't think of anything suitable. But if you notice down here, that is not 42. But it is the 2's complement version of 42, which I did look up minus 42, and I came up with a value of which I have written down here of minus 42 in binary in 2's complement is 110101110, which funny enough just happens to be that value, which is quite good. I hope this has been informative, and I plan to do a number more of these demonstration boards. If you want the PCBs and other information is available on my GitHub webpage, a link to which is down below. Do take care.